Welcome to this problem-solving session. Today, we'll tackle the coding problem titled Prime Palindrome, which challenges us to combine two fascinating concepts, prime numbers and palindromes. Together, we'll explore how to efficiently solve this problem step by step. Let's dive in. In this problem, we are tasked with finding the smallest prime palindrome that is greater than or equal to a given integer, n. A palindrome is a number that looks the same when reversed. For example, 121 is a palindrome, but 123 is not. Similarly, a prime number is a number greater than 1 that can only be divided evenly by 1 in itself, such as 2, 3, 5, and 11. The input to our function will be an integer n, where n lies between 1 and 10^8. Our output will be the smallest number that satisfies both conditions. It must be a palindrome and a prime, and it must be at least as large as n. Let's look at an example to clarify. Suppose the input is n equals 6. In this case, we need to find the smallest number that is both a prime and a palindrome, and that is greater than or equal to 6. The first prime number that meets this condition is 7. Since 7 reads the same backward as forward, it is also a palindrome. Therefore, the output in this case is 7. Now consider a second example where the input is n equals 8. Starting from 8, the first prime number we encounter is 11. Unlike 9 or 10, which are not prime, 11 satisfies the conditions of both being a prime and a palindrome. As a result, the output is 11. Finally, let's examine a slightly more complex case where n equals 13. Here, 13 is the first prime number greater than or equal to 13, but it is not a palindrome because it does not read the same backward. The next prime number after 13 that is also a palindrome is 101. This makes 101 the smallest prime palindrome greater than or equal to 13. Additionally, the problem guarantees that a valid answer always exists and will be less than 2*10^8, so we can focus on implementing an efficient solution that handles all edge cases, such as small values like n equals 1 or large values close to 10^8. To tackle the prime palindrome problem, the most straightforward approach is the brute force method. Here, we start from the given number n and examine each subsequent number to determine if it meets two criteria, being a palindrome and being a prime number. First, to check if a number is a palindrome, we convert the number to a string, reverse the string, and compare it to the original. Second, to determine if the number is prime, we verify that it is greater than 1 and that no integer from 2 up to its square root divides it evenly. While this brute force method is intuitive and easy to understand, it is computationally expensive. The dual checks for palindrome and primality need to be performed for every number, leading to inefficiencies, especially for large values of n. To improve the solution's efficiency, we can use several key observations to optimize our approach. First, palindromes have predictable repetitive structures. Instead of checking every number, we can directly generate palindromes by leveraging this symmetry. For example, in odd-length palindromes, the first half of the digits determines the second half. Second, even-length palindromes greater than 11 are never prime because they are divisible by 11, making them unnecessary to consider. Lastly, we can skip redundant checks altogether. If a number is non-prime or non-palindromic based on these properties, we can avoid further examination. By generating only odd-length palindromes starting from n and testing their primality, we significantly reduce the search space and focus solely on valid candidates. This approach is far more efficient compared to brute force. The optimized approach is the preferred strategy for this problem because it reduces time complexity while remaining practical for large input values. The algorithm begins by addressing the simple cases. If n is less than or equal to 11, we can directly return the smallest prime palindrome, as all single-digit primes and 11 are valid. For larger values, we generate odd-length palindromes starting from n. This involves iterating over the first half of the number, mirroring it, and constructing palindromes like 101, 111, and 121. Each generated palindrome is then checked for primality using an efficient method, such as trial division up to the square root. As soon as we find a prime palindrome, we return it immediately, ensuring minimal redundant computation. When comparing the two approaches, we see clear trade-offs. The brute force method is simple and easy to implement but becomes extremely slow for large values of n due to unnecessary checks for both primality and palindromic structure on every number. In contrast, the optimized approach focuses only on valid candidates by leveraging the structural properties of palindromes and the mathematical properties of primes. This makes it significantly faster and more scalable, especially for constraints as large as n up to 10 to the power of 8. However, the optimized approach does require slightly more complex implementation steps, such as palindrome generation and skipping even-length palindromes. Overall, the optimized approach is the superior choice for solving this problem efficiently and effectively. To solve this problem, we need to identify the smallest prime number that is greater than or equal to a given integer, n, and also ensure that this number is a palindrome. Let's break this down further. A prime number is any number greater than 1 that can only be divided evenly by 1 in itself, such as 2, 3, 5, or 11. A palindrome, on the other hand, is a number that reads the same forward and backward, like 121 or 1331. Combining these properties, we are looking for a number that satisfies both conditions. To approach this, we can start by understanding the requirements. First, the number must be at least n, second, it must be a palindrome, and finally, it must be a prime number. This means that for any candidate number, we need to verify these two properties before determining if it's the solution. One straightforward way to solve this is through a brute force approach, where we iterate through all numbers starting from n and test each one for both the palindrome and prime properties. While this approach is simple, it offers a good foundation for understanding the problem and can later be improved upon for efficiency. The brute force approach begins by initializing a variable called candidate to the value of n, which represents the starting point for our search. First, we check if this candidate number is a palindrome. To do this, we can convert the number into a string, reverse the string, and compare it to the original. If the reversed version matches the original, the number is a palindrome. Next, we need to check if the candidate is a prime number. This involves verifying that the number has no divisors other than 1 and itself. To test for primality, we iterate through potential divisors from 2 up to the square root of the number. If any of these divisors evenly divides the number, it is not a prime. If the candidate passes both the palindrome and prime checks, we return it as our solution. Otherwise, we increment the candidate by 1 and repeat the process. To make this approach more efficient, there are a couple of optimizations we can introduce. For the palindrome check, instead of converting the number to a string, we can reverse it mathematically by extracting and appending digits, which avoids the overhead of string operations. Similarly, for the prime check, we can skip even numbers after checking 2, since all other even numbers are inherently not prime. We also limit divisor checks to the square root of the number, as any larger divisors would have already been paired with smaller ones. There are several insights that can help us better understand this problem and optimize the solution. First, the palindrome property is inherently symmetric, meaning that reversing the number provides a straightforward way to verify it. Second, while checking for primality can be computationally expensive, limiting divisor checks to the square root of the number and skipping even numbers significantly reduces the time required for this step. Combining these two conditions, being prime and a palindrome, is relatively rare, so in practice, the number of iterations required to find a solution is often small. When it comes to implementation, we don't need any additional data structures. The entire algorithm operates directly on the candidate number using simple integer variables to store intermediate results. As for complexity, the palindrome check has a time complexity of O(d), where d is the number of digits in the number. The prime check takes O(sqrt) n for each number tested. When we consider the worst case, where the algorithm tests multiple candidates, the overall complexity is O(k*) sqrt n plus d, where k is the number of candidates tested. This gives us a clear understanding of the trade-offs involved and highlights areas where further optimizations could be applied if needed. Here, we define a class called solution with a method prime palindrome. Inside this method, we define two helper functions. The first function is _palindrome, checks if a number is a palindrome by converting the number to a string, reversing it, and comparing it with the original string. The second helper function is _prime, determines if a number is prime. It handles edge cases like numbers less than 2, and explicitly checks small primes like 2 and 3. For other numbers, it uses a loop to test divisibility by integers up to the square root of the number, skipping multiples of 2 and 3 for efficiency. After defining these helpers, we address a few special cases. If the input n is less than or equal to 2, we immediately return 2 since it is the smallest prime palindrome. Similarly, for inputs up to 7, we check against the single-digit primes 2, 3, 5, and 7 and return the first one that meets or exceeds n. Next, we handle cases where n is greater than 11. Since even-length palindromes larger than 11 cannot be prime, we adjust n to the smallest odd-length number greater than or equal to n if it has an even number of digits. Then, we enter a loop that continues indefinitely. Inside the loop, we check if n is both a palindrome and a prime using the helper functions. If both conditions are true, we return n as the result. Otherwise, we increment n by 1 to test the next candidate. Additionally, if this increment causes n to reach an even-length number, we skip directly to the next odd-length number by setting n to 10 raised to the power of its new length, plus 1. This ensures our search remains efficient by avoiding unnecessary checks of invalid candidates. Here, we start by defining the prime palindrome method, which takes an integer n as input. Within this method, we first implement a helper function called isPalindrome to determine if a given number is a palindrome. This is achieved by converting the number to a string and using two pointers, one starting from the left and the other from the right. The pointers move toward the center, comparing characters at each step. If any mismatch is found, the method returns false, otherwise, it returns true once all characters are successfully checked. Next, we define another helper function, isPrime, to check whether a number is prime. This function handles edge cases, such as numbers less than 2, and optimizes the prime checking process by testing divisors up to the square root of the number. It skips unnecessary checks for even numbers and multiples of 3, reducing computational overhead. The method returns true if the number passes all checks, and false otherwise. The implementation proceeds by addressing special cases. First, if n is less than or equal to 2, the smallest prime palindrome, which is 2, is returned immediately. Next, if n is within the range of single-digit primes, such as 2, 3, 5, or 7, we iterate through these values and return the first one that is greater than or equal to n. This ensures efficiency for small inputs. Additionally, for numbers larger than 11, we account for the fact that even-length palindromes greater than 11 cannot be prime. To handle this, we adjust n to the next odd-length number by calculating the smallest power of 10 that exceeds the current number and adding 1. This ensures our search begins with valid candidates. Finally, we enter a loop where we check if the current value of n is both a palindrome and a prime using the helper methods defined earlier. If both conditions are satisfied, the number is returned as the result. If the current number n fails either the palindrome or prime checks, we increment n and continue the loop. To maintain efficiency, we skip even-length numbers entirely. This is done by checking the length of n after each increment. If the length becomes even, we immediately jump to the next smallest odd-length number by calculating the appropriate power of 10 and adding 1. This ensures that the search space remains focused on valid candidates. Since the loop continues indefinitely, it guarantees that the first valid prime palindrome greater than or equal to the input n will be found and returned. This approach balances correctness and efficiency, leveraging the helper methods and special case handling to minimize unnecessary computations. To solve this problem, we start with the input value n equals 8. Our goal is to find the smallest prime palindrome that is greater than or equal to n. First, we check if n is less than or equal to 2, but since n equals 8, this condition is false. Next, we check if n is less than or equal to 7, which is also false. This means we proceed to the general computation loop. Here, we ensure that we are working with odd-length numbers. For now, since n equals 8 is even length, it's valid to proceed. The first step in the loop is to check if 8 is a palindrome using the function is_palindrome. This function checks if the string representation of 8 is the same as its reverse, which it is, so the result is true. However, when we check if 8 is a prime number using the is_prime function, we find that it is divisible by 2, so it is not prime. At this point, we increment n to 9 and repeat the checks. For n equals 9, it is a palindrome, but it is not prime since it is divisible by 3. We then increment again to 10, which is not a palindrome, so we skip the prime check. Finally, when n reaches 11, it is both a palindrome and a prime number, so we return 11 as the result. Now, let's work through an example with the input value n equals 13. As before, we first check if n is less than or equal to 2 or 7. Since neither condition is true, we proceed. Here, n equals 13 already has an odd length, so no adjustment is needed, and we move forward. The first step is to check if 13 is a palindrome using the is_palindrome function, which returns false. This means we increment n to 14. Again, 14 is not a palindrome, so we skip the prime check and increment to 15. The same holds for 15, 16, 17, 18, and 19, as none of these numbers are palindromes. At this point, we increment n to 101, the next odd-length number. This time, 101 passes the palindrome check, and when we check if it is prime using the is_prime function, it also passes. Therefore, the smallest prime palindrome greater than or equal to 13 is 101, and we return this as the result. Finally, let's consider the input n equals 120. Since 120 has an even length, we adjust to the next odd-length number, which is 1001. We then check if 1001 is a palindrome using is_palindrome. The result is true, so we proceed to check if it is prime using is_prime. However, 1001 is not a prime number as it is divisible by 7. From here, we increment n to 1002 and adjust again to the next odd-length number, which is 10001. Checking 10001, it is a palindrome, but it is not prime. We continue this process, incrementing and adjusting as needed, until we find the next valid case. Eventually, we discover that 10301 is both a palindrome and a prime number. Therefore, the smallest prime palindrome greater than or equal to 120 is 10301, and we return this as the result. To analyze the time complexity of our solution, we start with the key operations. First, the is_palindrome function checks whether a number is a palindrome. This involves converting the number to a string and reversing it, which takes time proportional to the number of digits in the number, represented as O(D). Next, we have the is_prime function, which checks if a number is prime. This process begins with a few constant time checks for small values but primarily involves iterating through possible divisors up to the square root of the number. By skipping unnecessary checks and incrementing in steps of 6, this loop runs approximately O(x) iterations, with each iteration performing a constant time modulo operation. Thus, the overall time complexity for the primality check is O(x). Additionally, to optimize further, the algorithm skips even numbers and numbers with even lengths, ensuring we only evaluate odd-length numbers. This efficient progression minimizes unnecessary computations and contributes negligibly to the overall runtime. Now let's focus on the main loop of the algorithm. In the worst-case scenario, the algorithm incrementally checks each number starting from n until it identifies the smallest prime palindrome. For each candidate number, two operations are performed, a palindrome check, which takes O(D), and a primality check, which takes O(n). Combining these, the cost per iteration becomes O(D) plus (n). The total number of iterations depends on the gap between the input n and the next prime palindrome. For smaller inputs, the iteration count is relatively low. However, for larger inputs, the number of iterations is primarily determined by the distance to the next prime palindrome. To determine the overall time complexity, let n represent the value of the resulting prime palindrome. Since the number of digits in n is log 10 n, the total cost is given by the product of the number of iterations and the cost per iteration. This yields a complexity of O(n) log 10 n plus (n). In the worst case, this simplifies to approximately O(n), where n is the first prime palindrome greater than or equal to n. Switching to space complexity, the memory usage of the solution is highly efficient. Starting with the is_palindrome function, converting a number x to a string and reversing it requires additional space proportional to the number of digits in x, which is O(D). Here, D represents the number of digits. For the is_prime function, the primality test operates in constant space, using only a fixed number of variables for calculations and checks. No additional data structures are employed. As a result, the overall space complexity of the algorithm is dominated by the string conversion in the palindrome check, leading to O(d) space usage. Since the number of digits d in a number n is equivalent to log 10 n, the total space complexity simplifies to O log 10 n. This ensures that the solution remains space efficient, even for large inputs. To understand the advantage of this approach, let's compare it to a naive solution. A brute force method would involve iterating through all numbers starting from n, checking if each is prime. Since this approach does not restrict checks to palindromes, it would waste significant time on non-palindromic numbers. The primality test alone would require O(sqrt) x for each number, resulting in a time complexity of O n *sqrt n without any optimizations. In contrast, our optimized approach drastically reduces the number of iterations by focusing only on palindromic numbers and skipping even-length numbers entirely. This refinement ensures the algorithm is computationally efficient, even for larger inputs. The mathematical reasoning behind the big O complexity lies in the interplay of palindrome and primality checks. By leveraging the properties of palindromes and primes, the algorithm narrows down the candidates, achieving a worst-case time complexity of O n *sqrt n. Meanwhile, the space usage remains minimal, with a complexity of O log 10 n, thanks to the absence of additional data structures. Together, these optimizations make the solution both time and space efficient. When solving the prime palindrome problem, there are several common mistakes to watch out for. First, not accounting for edge cases like n equals 1 can lead to incorrect results. Remember, 1 is neither a prime number nor a valid palindrome, so you need to skip directly to the next valid number, which is 2. Another frequent issue is using inefficient methods for checking primality, such as looping all the way up to n instead of optimizing with a square root approach. This can severely impact performance for larger inputs. Then, there's the mistake of ignoring even-length palindromes. While most examples focus on odd-length palindromes like 121 or 12,321, even-length ones like 1221 might still need to be considered, depending on the problem's constraints. Additionally, when reversing numbers to check for palindromes, be mindful of potential integer overflow, especially with larger inputs. Lastly, some solutions miss out on optimization opportunities by separating palindrome generation from primality testing. These processes can often be combined to reduce redundant checks and improve efficiency. Now, let's consider the interview context and key insights. This problem is designed to test your ability to optimize multiple tasks simultaneously, as it combines the concepts of palindrome generation and primality testing. A strong solution doesn't just solve the problem but also minimizes the number of checks for both palindromes and primes. Techniques like the sieve of Eratosthenes can be used to pre-compute primes, while specific strategies for generating palindromes can make your solution more efficient. It's also important to discuss trade-offs during an interview. If you use a brute force approach, make sure to acknowledge its inefficiencies and suggest alternatives. This demonstrates your understanding of different strategies and their benefits. Additionally, explaining how you handle edge cases, like n equals 1 or very large inputs, is essential. Clarity in addressing these edge cases can set you apart. For further practice, you might explore related problems like LeetCode 9, which checks if a number is a palindrome, or LeetCode 204, which involves counting primes up to n. These problems reinforce the core concepts you're applying here. Finally, let's explore some alternative approaches to solving the problem. A straightforward brute force method involves iterating through numbers starting from n, checking each one for both palindrome and primality. While this is simple to implement, it's inefficient for large inputs due to its O n *sqrt n complexity. A more optimized approach is to pre-compute primes using the sieve of Eratosthenes. With this method, you can iterate only over primes to check for palindromes, achieving a time complexity of O n log n for the sieve and O n for palindrome checks. However, this approach uses more memory, so there's a trade-off. Alternatively, you can generate palindromes directly by mirroring digits and then check primality only for these candidates. This reduces redundant checks, but the implementation requires careful handling of the palindrome generation. Another option is to pre-compute palindromic primes and use a binary search to quickly find the smallest one greater than n. This method offers fast query performance, but the pre-processing step can be expensive. Each approach has its strengths and weaknesses, so the best choice depends on the problem constraints and your specific needs. Great job! In this session, we learned how to solve the prime palindrome problem by combining mathematical intuition with efficient coding practices. Remember, mastering problems like this prepares you for real-world challenges and interviews. Thank you for joining, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!